Hello students, today we're going to talk about acid-base titration curves, and we're going to look at the way that we find pKa's of weak acids. And this is one of the major ways that we do this, is to take a weak acid and react it with sodium hydroxide. And what are we trying to do there is we're trying to make the conjugate base. Okay, so here's NaOH. So that's hydroxide. I'm going to abbreviate it as hydroxide, and I'm going to ignore the sodium ion as a spectator. Remember that breaks apart into ions, but I think talking hydroxide is more simple. Now, unfortunately, depending on when you took your previous course, you may or may not remember very well your titration. And I'll have a link to an animation and also a video of a real titration in case you don't remember. But normally what we do is we add into this flask via a burette NaOH. Okay, now the hydroxide will react with the acid. So let's write that, plus OH minus, to neutralize it. So this is a neutralization. Acid plus base. Okay, so just like we practiced before, when it loses H plus, it's just one at a time. So this will make water and HSO3 minus. Okay, now notice this is weak acid and this is conjugate base. Okay, now a couple things. In the titration, this is like a snapshot of what's happening at every moment. So here's the H2SO3. This is what we have initially. And going over here to this graph, you see this first red dot. That would be the initial acid pH. So on this side, what we're doing is we're tracking pH, which is listed here. Okay, now when we add base, the pH will go up because you're adding a base. And ultimately, you're going to get to the point, and I'm going to draw it in a little flask over here, where you just have HSO3 minus. That would be here, this dot here. Okay, that's where you have only conjugate base. And that is, in these diagrams, going to be the midpoint of this steeply rising part. You see how this goes up sharply? The midpoint of that is where you have only conjugate base. Now you see where it says pH equals to 4.24? That's actually red on the y-axis in pH. Now this is going to be really tough, but if I could have any chance of doing this, it would be something like this. Oh, not too bad, not as bad as I thought. It's a little tilted upwards, but if you had this, let's say on an Excel file, you could read that point, which is essentially what they did. So that's reading 4.24, but that is over on this axis. That's where you have only conjugate base. You see how it's just HSO3 minus. Now, along the way, let's look at it this way. Initially, you have 100% H2SO3, and then here at equivalence point, you have 100% conjugate base. Okay, now equivalence point is really then where you are fully neutralized. Okay, now along the way, as we go from just acid to just conjugate base, see here, this path that we're taking, along the way, you have what we would say is a mixture of weak acid and its conjugate base. And what do we call a mixture of weak acid and conjugate base? Is we call that a buffer. So you see here where it says buffer region, that's because in that area, you have a mixture of both weak acid and its conjugate. Now recall that the pH that that solution has will depend on the ratio of A- to HA relative, and it also involved is our pKa. Now also remember that if our ratio of A- to HA is 1, pH equals pKa. Now on this titration curve, where are we going to end up with that ratio of 1? It actually will turn out to be when I have 50-50 of weak acid and 50% conjugate base. When that happens, the pH equals the pKa. So what I'm trying to get you to think of is that these titration curves track the process of going from initially just weak acid, then you get to the point where you have a mixture in the buffer, and then you have a point where you just have base. So let's take a look up at the graph then. Initially, just weak acid, we keep adding base, keep adding base. Then we hit this point here where it's highlighted in red. You see where it says base equals weak acid? That's our 50-50 point. That's where these two are equal to each other. When that happens, our ratio is 1. And our pH equals pKa. So the pKa, we would read off the graph at this point here that I'm highlighting. If you go over, so if you highlight it going over, it would hit 1.85. And that's our initial pKa, or pKa1, I should say. So let me highlight that if I can. We're going from this point over to the graph there. And this whole area here is the buffered region. Now, putting this into perspective, though, do you recall what our criteria is for a functional buffer? What range will it be effective? Plus or minus 1 unit from pKa. So if the pKa is 1.85, this guy would be buffered between 0.85 and 2.85. And probably, let me redraw that because that's not going to be exactly correct there. Sorry, I got a little carried away with my highlighter. Let's see, I think I need an eraser. Sorry. Let me re-highlight this, okay? At first, I used it to highlight where it hit the axis. So recapping then, 1.85 is where this midpoint hits this line over here. And then I'm going to go back and highlight the plus or minus 1 unit from that pKa, which is this region here that's buffered. Okay, and now a couple comments that are important is, let's say, okay, a couple very important. At equivalence point. At equivalence, let's draw down. It's going to hit here at 40 mils of base. That's how much volume it would take for this particular titration. Looking up at the info on what we're titrating, it's a 0.1 molar, 40 mils of weak acid, and we're titrating with 0.1 molar NaOH. So it'll take 40 mils. Now, I'm not going to ask you for that math, but just as a side note for those of you that like the math, where does those numbers come from? It would come from stoichiometry, 1-to-1 mole ratio. So what if you have the same concentration of acid and base, then the volumes would be the same to neutralize it. Okay, so if it took 40 mils to reach that point, this 50-50 mark will be when you're half neutralized. So then we would know that that's at 20 mils. Oops, I drank way too much caffeine this morning. Boy, that is a terrible drawing. I have to laugh at that guy. That one wasn't good. So let me try one more time to do a little bit decent. Okay, so 20 mils would give us this 50-50 mark. Okay, this is always true. So what I have just drawn is always true. So if it takes 40 mils to get to the equivalence point, it'll take 20 mils to get to pH equal to pKa, this 50-50 mark. Let's imagine that it took 100 mils to get to equivalence. That would mean at 50 mils, it would reach the 50-50 mark. So this relationship is always true, that this 50-50 mark is the half neutralized point. Okay, the other thing, and I'm going to pick a different colored pen for this, purple. We're not always at the 50-50 mark. So if I put, let's say, this point here, and I want to know what is going on at that mark, okay, notice that at that point, let's think about it, we are not at 50-50, we're somewhere in here. Maybe just roughly, it kind of looks like I'm at 75% acid, 25% base. Okay, now notice that in that case, we are going to have more acid and less base. So in that case, we're going to see that the pH is less than the pKa. Okay, and that's what we talked about with buffers, is that in a buffer where you have more weak acid than base, the pH will be less than pKa. Now, those of you that love the math, you can calculate it. You could plug in 25 to 75. Okay, and then you'd get what pH you're at exactly. You could read it off the graph if we had a better marked graph. Okay, now let's take a different point. Do a different colored pen. Let's do green. Let's say I want to know what's going on at this point here. That is most likely over on this side here, the green. That would be maybe 75% base, 25% acid. And in that case, what would happen is that we would see, I'm going to put this over here in green, we'd have more A minus than HA. So pH would be greater than pKa. Okay, so one last thing before I move on from here is that the buffer region just as a highlight, the buffer region is plus or minus 1 unit from the pKa. Our first pKa here from the graph is 1.85. So the buffered region would be 0.85 to 2.85, which would actually correspond to a wider range than I initially showed you. So let me re-highlight that. So if we're looking at 0.85, really the buffer region is extending, right? And so let's look, maybe I did it a little bit too high there. So that's 3, so it'd actually be a little bit lower. Let me erase it. Our best buffer is in that range. So it would be about 0.85 all the way to about 3. So I'm going to put it there, okay? And what's kind of interesting is I would have thought their little brackets that they had for buffer region would correspond, but I feel like this one bracket's a little low because it's really this range, 2.85 to 0.85. And I'm sorry, that's where I got a little confused because you see how they had it with brackets? This bracket seems lower than 2.85, but maybe from their Excel file that corresponded to it. Okay, so just keep in mind that with a better graph, we'd be able to pinpoint that a little bit better. This graph's not as well marked, okay? All right, so take a minute. This is a lot of info. The one that I did on the Zoom discussion, I did one on Zoom on 8/25. If you go to the Zoom discussion link, you'll be able to access the recording from the Zoom discussion. And that one, I also introduced this, but I did phosphoric acid. So it's good because then it gives you another perspective, another acid to think about. Okay, now pause me if you have to and kind of rethink this. And then after you've thought about it, what I'd like you to do is to think about what we're going to do next, which is the second ionization. And I think that I can go to the next slide. I planned ahead. Let me check, okay? Oh, no, I thought I had copied it twice. Maybe, I wonder if I can do that while I'm talking to you. Okay, so pause me. No, it won't let me on this. Okay, so let me erase this. You can pause me and then fast forward me. I'm going to erase these formulas. I'm going to keep some of it because the concepts will be really similar. Okay, great. I didn't have to erase too much. Okay, so let's go back through now for the second part. Initially, we start at this fully neutralized point, but we're not done yet. We have HSO3 minus. And we're going to keep adding hydroxide. I should have said this earlier, but H2SO3 is a weak acid. Please don't confuse it with phosphoric, which is H2SO4. So hopefully you weren't thinking, wow, why is this a strong acid? It's not, it's a weak acid. Okay, this will make water and sulfite ion, SO3 2 minus. So initially, as we keep adding base past the first equivalence point, here we go. Adding base, adding base, adding base. Keep going, keep going, keep going. And then we'll hit the second equivalence point. At the second equivalence point, we only have sulfite ion. 100% conjugate base. And let's see if I can draw a straight line with this. Oh, this is so challenging. Oh boy, that was a terrible start. I think I do better when I try to do the dots. How's that? Is that okay? So notice that for second equivalence, it took 80 milliliters. Okay, so at second equivalence, you have sulfite ion, which I've shown here. In between the initial point, which was here, the first equivalence, okay, HSO3 was the base for H2SO3, but now HSO3 negative is now the acid for the next ionization. So that guy is going to continue to ionize. Initially, we just have HSO3 minus, and then we keep adding base, and then you hit that 50-50 mark where HSO3 minus equals SO3 2 minus, and at that point, pH equals pKa, half neutralized. We take this point here and we read off of the y-axis, and our pKa2 is 7.19. That means that the buffer region is 6.19 to 8.19. So let's see, highlighting that on the graph, 6.19 would be somewhere here, and then it would go to 8.19. Do you see how that's why I am going to complain a little bit about these lines. I think it was very, it's a little off because we want the buffer region to be between 6.19 and 8.19. So I hope that that's not confusing to you. I can address that on next Tuesday's Zoom, but it's within that range. It's just the graph. They were kind of stingy with the lines on drawing them because it should be a little bit further out from where they have those two lines within this range that I've highlighted in yellow. Okay, so a couple comments then. Notice that this has a look to it, that a proportionality to it. So if we started at 40 mils right here with HSO3 minus, and then fully neutralized was 80, the halfway mark is 60 mils. See how that's halfway? That's where pH equals pKa. So that'll always be true, that the halfway mark is where pH equals pKa. The other thing to kind of think about then is, again, we're going to practice this more with amino acids next week, is I'm going to use a different color pen. How about blue? Let's say I ask the question, oh, what's floating around in this region that I've highlighted with X? Okay, that spot, that's going to have more HSO3 minus than and less SO3 2 minus. You see how we're not quite at the point where they're 50-50. So the pH would be less than the pKa. And that's the second pKa, because that's what we're referencing, is that second mark. Okay, let's do one more. Let's say I had, let's see what color we can use. Let's go with purple. Say I'm here. And I'm going to erase this part. Thanks for bearing with me on all these erasing and stopping, but I do feel it kind of makes it a little bit more like real life instead of me just being a robot and reading off the slides. Like I just don't think that that's like helpful. You can read on your own, right? So anyways, a little more real life with all this pausing. So here's the X spot. See how that's past pKa2? So that would be a scenario where you have more A minus, less HA. Again, the A minus would be the sulfite, and the HA is HSO3 minus. So the pH is greater than pKa2. Okay, so to recap, you can pause me and you can rewind me, whatever you need to do. I'm going to erase right now. And I just want to clean this up and just highlight it one more time, like a recap, but from a clean graph. And we need this because we're going to be talking about amino acids, and amino acids have these titration curves. And so if you can understand these for like regular acids, it just makes it so much easier. Okay, so I'm looking at this titration curve. This is a base is being added to a weak acid, and we're judging the pH. We're monitoring the pH. And so initially our pH is low because it's a weak acid and an acid. Then we keep adding base. So the first thing I would note on these is that equivalence point. I'd highlight where that midpoint of this inflection is. At first equivalence, you always have only conjugate base. If it took 40 mils to get to equivalence point, halfway there at 20 mils, conjugate base equals weak acid, and pH equals pKa. In that case, it's pKa1 for the first ionization. And then the buffer region would be between 0.85 and 2.85. So we'd have to kind of read that off of the graph as along the way, as we go from just weak acid to conjugate base, we have this buffer region. But the special point of that buffer region is where pH equals pKa, where conjugate base equals weak acid. Next, as HSO3 now, it was the conjugate base for the first ionization. Now it's a weak acid. We're going to keep adding base until we reach the second equivalence point. Second equivalence point, again, is where we have only SO3 2 minus, which is sulfite. If it took, remember, look at that, that's the midpoint of that part. If it took 80 mils, sorry, I went to the side on my little dashed lines. I know, nutritionists, I drink too much coffee. I know that to be true. Okay, so gonna drop that. Okay, that was pretty good. Oh my gosh, that was amazing. Okay, so that's 80 mils of base. Halfway between 40 and 80 is 60. That's where we would have the spot. You see how it's the flat midpoint between the two sharply rising points. That's where we would read across on the y-axis, and pH equals the second pKa. The buffer region would be plus or minus 1 unit of that, 6.19 to 8.19. And the part of this that is important is that this tells us this type of technique will allow us to figure out the pKa of an acid, pKa1, pKa2, if there was a third, pKa3, and also gives us a good perspective on what's floating around in there at a certain pH. Now, here's what's interesting with this one is in biochemistry, the pH that we're most concerned with is pH 7.4. So if I come to this graph and I try to find 7.4, it's kind of roughly somewhere in here. And I go across, I'm within that buffer region. So as far as HSO3 minus and SO2 minus, at pH 7.4, you have pretty close to 50-50, a little bit more base than weak acid, right? Because you're above 7.4 is a little bit above, right, pKa2. So at pH 7.4, we have more SO3 2 minus than we do HSO3 minus. It's right past that 50-50 mark. And that's one thing that we're going to talk about as we move forward with the amino acids. Okay, let's go to the next slide. Here's another one. This is just a recap of these. You can take a look again that if in this case, here's the equivalence point for this titration. This is formic acid to formate. Then halfway there, pH equals pKa. And then the buffer region lies within plus or minus 1 unit of the pKa. So the buffer region's within that range. Okay, so this is a titration curve for a polyprotic acid generic. If you want to practice identifying the equivalence points and where pH equals pKa, take a minute and then I will highlight them for you. So pause me, do this one as a test, and then I'll go over it. So pause. All right, so you're back with me. And so what I'm going to highlight here, and I'm going to pick, I think a red, is my equivalence point is here, the midpoint at 20 mils. And here's another equivalence point. This one's not as dramatic, 40 mils. So this would be first equivalence point, second equivalence point. So if the first equivalence point is at 20, halfway there would be here at 10. And if I read across to this pH, pH equals pKa1 at that X that I've marked. Looks like it's probably somewhere around 2.5-ish. Okay. All right. And then my second pKa, not equivalence, pKa would be here at 30. And I read across. That one's easier to read. It looks like my pKa2 is 10. Okay, so recapping then, pKa1 looks like every marking is, that's about 2.5. So the buffer region would be 1.5 to 3. pKa2 is at 10. So the buffer region would be between 9 and 11. And what I liked on that other graph that might make it a little bit easier for us is we could highlight, if you wanted, the buffer region again. So that would be for the first one, 1.5 to around 3. So that is this range here, right, of values. Oops. Okay, so I prefer if you just highlight your buffer area, just note it here instead of trying to use these graphs that are harder to read. Okay, the graphs that we would normally collect as a student, they'd have it using Excel, and so you could clearly highlight the buffer region and not have to eyeball it. So I'm going to erase this here, but that could be another way of doing it if you wanted to. Okay, and then, all right, so hopefully, now this did not tell us what our polyprotic acid was. It has 2 equivalence points, so we would assume that it has like a, let's call it generic H2A. So we could say initially we have H2A. At first equivalence, it's its conjugate base of HA minus. pH equals pKa, 50% H2A, and that's equal to HA minus at that first round. For the second one, HA minus equals A2 minus. So we start off with HA minus, we end up at A2 minus. And this marker is where H2A equals HA minus. Okay, great. For more practice and more discussion, go to the Zoom discussion where I did phosphoric acid. And we will need this for chapter 4, so that's why we were going through it kind of extensively.